Hi everybody, welcome back. We're on section 7-8 in our textbook, and what section 7-8 really deals with is the idea of a fourth quantum number. Remember, we have n, we have l, we have m sub l, and this fourth quantum number, as you can see here, is called your m sub s. It's your electron spin quantum number, and it was generated because it was deemed necessary based on the emission spectra of atoms to have a fourth quantum number to explain their behavior. When you place a spinning charge like an electron, so an electron spinning produces a magnetic moment depending on the direction in which it's spinning. It can spin clockwise or counterclockwise. And if it spins one way, we believe it produces one magnetic moment, say a north pole. And if it spins the other way, we believe it produces another magnetic moment, say a south pole. And so there's really only two values for the magnetic spin quantum number. And they are, if the electron is spinning up, then, or say clockwise, we give it an up arrow, and its m sub s value, as you can see here, will be plus 1/2. However, if it's spinning counterclockwise, then its m sub l value would be minus 1/2. And when we draw those in our orbital diagrams, if you remember, if it's spinning clockwise and it has an m sub s plus 1/2, we simply just give it the up arrow. However, if it were spinning down, we would give it, and it doesn't, I put it there only because it's easier to draw with this thing, we would give it the m sub s value of minus 1/2. So there's a fourth quantum number. In addition to the energy level, the n, the sublevel, the s, the orbital, the m sub l, now we can state in what direction the electron is spinning. And an electron can spin in only one of two opposite directions. And this led to the idea of the Pauli principle. And the Pauli principle basically states, that in a given atom, no two electrons can have the same four quantum numbers. So if you have an atom that only has an s sublevel, which only has one orbital, which can hold two electrons, those electrons must have opposite spins. That way they have a different m sub s value. So no two electrons can have the same four quantum numbers. Every electron will have a unique set of those four numbers. That's the Pauli exclusion principle. No two electrons can have the same four quantum numbers. Okay. Section 7-9 deals with issues that arose with our model when we looked at electrons that are elements that had more than one electron. They're called polyelectronic atoms. All that those are atoms. Oh boy. Yeah, I have a hard time writing on this. Hopefully my power is fixed when we get back to school. So these are atoms. How's this? That might work better. Okay, so they are atoms with more than one electron. What I'd like you to do actually is take a read through section 7-9, and your notes have some questions in it, and then we'll talk about what those questions are. So pause the video and then take a read through section 7-9 in your textbook. It's one of those super theoretical sections again, and then we'll go over the sections. I hope you actually took the time to read. We're back, and I just want to go over these questions. What are the energy contributions that must be considered when describing helium? Two of them are the same as hydrogen. You have to consider the kinetic energy of the electrons as they move around the nucleus. Hydrogen's electron also had kinetic energy, so we had to deal with the kinetic energy of that. The potential energy of the attraction between the positive nucleus and the electrons. We had to deal with that with hydrogen as well. Hydrogen's electron is attracted to the positively charged nucleus. What's unique about helium, because helium has two electrons is that this third one comes into play, the potential energy of the repulsions between the two electrons. So that is an issue that we have to deal with helium that we did not have to deal with hydrogen. That's a unique issue. What does your textbook mean by the electron correlation problem, and how do we deal with the problem? Since we don't know the way an electron moves, where it will be in space, we cannot calculate its repulsion value or energy of repulsion with the other electron, because we don't know where they are, we don't know how they're moving, we don't know when they're repelling, so we can't really calculate the electron repulsions. And so to simplify this is that we make approximations, and the simplest approximation we make is that we pretend that it is traveling in a field of charge. It is an average of the repulsions of the electrons, just based on the number of electrons there are, not necessarily where they are and when they experience those repulsions. I thought there was a question about degenerate orbitals somewhere. If you do have a question about degenerate orbitals, I'm going to add it in up here because I thought it was there. The term degenerate, when it comes to this stuff, actually means that all the electrons in a particular sublevel have the same amount of energy. Okay, so what that means is if I am, say, carbon, and I have 4 electrons in my p sublevel, they all have the same amount of energy. They are degenerate because all the electrons are in the 2p sublevel. Okay, why would it take more energy to remove an electron from Al plus rather than Al? It requires more energy to remove the electron because of the positive charge, which greater attracts the electrons, the nucleus and the electrons. There's a filling order, and we'll talk about that in just a moment, where we fill S, then P, then D, and F within a quantum level. And that's because we fill in order of lowest energy. But there are exceptions to that, and we'll talk about it. But S, P, D, and F within a sublevel all fill first. S, then P, then D, and F. Okay? So that's because S is lower in energy than P, which is lower in energy than D, which is lower in energy than F. All right, there's this idea of the penetration effect, okay? And I think the easiest way to explain the penetration effect is to take a look at one of these probability distributions, where the y-axis here is the probability. Basically, you can think of it as the amount of time they spend, and where they spend it is on the x-axis, their distance from the nucleus. So you can see by looking at this that S spends most of its time at a distance farther from the nucleus than P. However, you can see in following the path of S that while it spends most of its time there, there is a portion of time that it spends closest to the nucleus. And so because the S orbital, even though the electron in the S orbital spends most of its time farther away from the nucleus than P does, it is able to move closer at some point during its path, closer to the nucleus. And closer to the nucleus is lower in energy. So although S spends most of its time farther from the nucleus, the fact that it's able to penetrate through the P orbital closer to the nucleus is known as the penetration effect. And it is the reason why the S sublevel is lower in energy than the P sublevel, due to the penetration effect. The same thing also happens with 3D and 3P. If you take a look here, here's your S. It spends actually most of its time farthest from the nucleus compared to 3B and 3P, excuse me, and 3D. If you notice though, if this is distance from the nucleus, the sublevel that you'll find, at least an electron spending some of its time there, closest to the nucleus is 3S. And then the next closest to the nucleus sometimes is 3P. And then the next closest is, again, the 3s electron, and then the next closest we have 3d. So 3d starts to come in a little bit further from the nucleus. So the idea that an electron in the p sublevel can penetrate closer to the nucleus than an electron in the d sublevel is the penetration effect, and it results in lower energy. Okay, we'll stop this video now for here. That should have covered sections 7-9 and 7-8. If there are things you do not have filled in, go ahead and fill those in. We will be getting to the Aufbau principle, so don't wait for that. We'll come back. There will be at least 2 more videos coming up. Okay, we'll see you for section 7-10 next. Bye-bye.